Hello, everyone. I'm Zhang from Harbin Institute of Technology, China. On behalf of the authors, I will introduce our paper, Aperiodic Local SGD Beyond Local SGD. Let's first overview the process of distributed SGD. Distributed SGD is the core of the distributed deep learning. Suppose there are multiple workers and one server to train a deep learning model. Each worker calculates the gradients of model parameters. Then the gradients are sent to the server. Server updates model by one step and then sends the updated model back to the worker. This process goes on for many rounds, and at last, we can get the trained model. Obviously, we can find it requires massive computation overhead. One intuitive way to decrease computation overhead is reducing the synchronization frequency. That is, each worker iterates several times to update a model locally and send a local model to the server for synchronization once in a while. It is named local SGD or parallel restarted SGD or federated averaging in different scenarios. This figure illustrates the difference between SGD and local SGD in 3 dimensions: performance, communication overhead, and computation overhead. We can measure performance by loss value, communication overhead by synchronization times R, and computation overhead by iteration items. SGD usually get a model with better performance, especially in data non-RID case, and the convergence rate of SGD is slightly faster than local SGD. But SGD has much higher communication overhead than local SGD. It is intolerable in distributed training. Thus, in summary, local SGD is a trade-off among performance, communication overhead, and computation overhead. In the right figure, it illustrates the difference between SGD and local SGD. We can find local SGD largely reduce the synchronization times to adapt to distributed training. Moreover, since local SGD is the trade-off of 3 key factors, we eager to know the optimal balance that optimizing one factor with fixing the other 2. Concretely, we have this question: is performance fixed if the overhead is fixed? It seems no. Because when T and R are fixed, there still is an almost infinite number of synchronization schemes. For example, these 2 schemes below have the same cost as local SGD, but we don't know which one is best. So naturally, 2 questions arise. First, is the periodic synchronization scheme best, that is, with best performance? Second, if it's not the best, can we find a better one than local SGD? In order to solve this problem, we should formulate them first. We denote synchronization index as IT from 0 to T. Each item is a step of synchronization. Eventually, we denote local iteration number sequence as ET. The items in this list is a local iteration number in one round. These two indexes are equivalent. For local SGD, IT can be represented by this and ET like this. So based on these notations, we formulate our question into a mathematical optimization problem to minimize global loss subject to fixed communication cost and computation cost. To quantify performance, we introduce some assumptions which are all widely used in the previous studies. They are smoothness, quasi-convexity, and bounded variance. Based on these assumptions, we can model the loss and translate the initial optimization to this one. Here we get the upper bound of the loss. The details of the proof is in our paper. Considering the bound is reasonable, since a lower loss bound means potential to achieve better performance. Here, only the fourth items is related to IT. In another word, different IT or ET lead to different D. Thus, we only need to consider to minimize. So we translate the problem to minus D. Then from it, we can get the theorem. It shows a simple feature of an optimal scheme of ET. That is EI larger than E2 and larger than ER. That means the number of local iterations is getting smaller and smaller. As this figure shows, this conclusion answers the first question. Periodic synchronization scheme is not the optimal one. So we will consider the next question. Can we find a better one? For example, all these three schemes satisfy the conclusion that EI becomes smaller and smaller. But which one is our target to train a better model? It's hard to get the answer directly. So we add two reasonable assumptions. First, the learning rate is small enough. Second, delta I is much smaller than EI. Here, delta I is equal to EI minus EI plus 1. Based on these assumptions, we get this conclusion. The optimal ET is an arithmetic progressing with a negative common difference. So for a given local SGD, we can write down corresponding optimal ET of ALSGD like this. Until now, only two factors need to be determined. The first item, E star, and the common difference, DE. Based on the same T, DE can be determined by E star. Then, based on the assumption that delta is much smaller than EI, we can get the range of E star like this. For example, if we set H equals 10, we can translate local SGD to ALSGD by choosing E star in the range. Until now, we finished our analysis and can translate any local SGD scheme to ALSGD scheme. So far, we have answered the two questions and get a better strategy than local SGD. In the next, we will verify the analysis on real data sets. First, we compare our ALSGD with local SGD on two data sets, which are Siyao and F-MINIST. For ALSGD in each experiment, we choose two different E star. Both of them satisfy the range of E star discussed in the previous slides. We can find in non-ID scenarios, ALSGD outperforms local SGD, no matter what kind of data sets and hyperparameters, such as work number, synchronization times R, and T. In these three tables, we change the work number, T, and R, and data sets. ALSGD is always better than local SGD. And in ID scenarios, ALSGD and local SGD perform the same. It is the same as our analysis. From the upper bound of the loss, G is large in non-ID scenarios and is small in ID scenarios. So in ID scenario, IT has little influence on performance because the whole atom is close to zero. But in non-ID scenario, the impact of IT can't be ignored. So the difference between local SGD and ALSGD is obvious. The previous model we use are simple models, such as MLP and CNN with few layers. Then we compare methods by more deeper models and non-ID data. We compare the performance of ALSGD and local SGD on Siyao, Siyao 100, and Tingting using ResNet respectively. It shows that ALSGD obtains better performance, better model than local SGD, the same result as before. As a result, at last we investigate the condition about E star. We require E star in this range. It's based on DE is less than 0, and delta is much less than EI. Let's see if they are not satisfied. What will happen? In the left figure, the green line represents local SGD. The red dashed line represents ALSGD, where E star in the range. We can find in this situation, ALSGD outperforms local SGD. But if E star doesn't in this range, what will happen? First, we consider E star less than E. That is, we choose DE greater than 0. For example, we set E star is equal to 100, denoted by the blue dashed line. We can find the corresponding ALSGD underperforms local SGD. Furthermore, we consider another condition. If we set E star too large, at the last several rounds, EI is not large enough compared with delta. And the delta is so we shown by the yellow dashed line. The performance degrades rapidly at the end of the tree. These experiments verify the correctness of our analysis. So in the end, we conclude our paper. First, local SGD is not optimal. Second, we get ALSGD, which can obtain better model than local SGD with the same communication and computation overhead. Third, we get a way to transfer local SGD to ALSGD easily, just by changing the timing of synchronization. We also have some limitations in the work. For example, the assumption about gradients is a little bit strong and is not very intuitive for data heterogeneity. In future work, we will use more intuitive assumptions such as this to improve our work. Thanks.